Introduction to Inorganic Chemical Nomenclature Part 2, Polyatomic Compounds. This lesson was divided into two parts owing to its length. Part 2, Polyatomic Compounds. In this video, we will study the nomenclature of polyatomic compounds. Now, there is also a first video in which I presented the nomenclature of binary compounds, and you really should complete that first to understand this clearly. If you care to search for it, it's on YouTube under the name Inorganic Chemical Nomenclature, Part 1, Binary Compounds. The nomenclature of polyatomic compounds requires that we are familiar with polyatomic ions, and many of these polyatomic ions are derived from oxyacids. So we're going to spend some time now learning the oxyacids and the polyatomic ions that they produce. So first of all, what is an oxyacid? Well, an oxyacid contains hydrogen, oxygen, and another nonmetal. Now, many oxyacids are found in cleaning products, in fruits, in food ingredients, and industrial chemicals. Let's go through some examples. Phosphoric acid, H3PO4, is used to pickle steel. Pickling steel means dipping it in the acid to remove any rust from the surface and also to give it a phosphate protective coating. Phosphoric acid is also a flavor in root beers and colas. Sulfuric acid, H2SO4, is the electrolyte used in lead-acid automobile batteries, typically around 35% sulfuric acid. Carbonic acid is formed when carbon dioxide is dissolved in water. According to this equation, if you simply add the atoms together, 2 hydrogens, 1 carbon, 3 oxygens, you get the formula of carbonic acid, H2CO3. And carbonated beverages contain carbonic acid when CO2 gas is dissolved in it. A solution of 5% acetic acid, CH3COOH, in water is sold as vinegar. So there are 8 important oxyacids. Some of these exist with varying numbers of oxygen atoms. This is something you're just going to have to spend some time, write out, put on the hard drive. You need to learn these 8 main oxyacids and their salts. The main oxyacids all end with the suffix "ic." They're all ic acids, and they are highlighted in the tables below that follows. Now, a mnemonic that might help you remember them in order that is useful. A car never stays perfectly clean. So the first ic acid is acetic, A for acetic, car for carbonic acid, N for nitric acid, S for sulfuric acid, P for phosphoric acid, and C for chloric acid. Now that's only 6 oxyacids. There are 2 more, and they are bromic and iodic. And if you recall, chlorine, bromine, and iodine are all congeners in the same group 7A family, the halogens. And so whatever formula and name is written for the chlorine acid, they are completely analogous for bromine and iodine. So it's easy to remember. So the ic acids, CH3COOH is acetic acid. Only 1 acidic hydrogen on acetic acid. These hydrogens are bonded to carbon and are nonpolar. Carbonic acid, recall, was H2CO3. Nitric acid, HNO3. Sulfuric acid, battery acid, H2SO4. It's got 2 acidic hydrogens. Phosphoric acid, flavor root beer, has 3 acidic hydrogens, H3PO4. We have chloric, HClO3, and analogous to that we have bromic and iodic, HBrO3, HiO3. Now, some of these ic acids have what might be referred to as a younger brother. a smaller form with one less oxygen. So whereas the ic acids have the number of oxygens shown, the us acids have one less. For example, nitrous acid has HNO2 has one less oxygen than nitric acid. Sulfurous acid, H2SO3, has one less oxygen than sulfuric. Phosphorus acid, H3PO3, has one less oxygen than phosphoric. Chlorous acid, HClO2, has one less oxygen than chloric acid. Likewise, bromous and iodous acids each have one less acid than the corresponding ic acid. Now, there are a few of these oxyacids that actually have what might be referred to as a baby brother with two less oxygens than the normal ic acid, and they are called hypo-us acids. So hypo is the prefix and us is the suffix. And hypo, if you know, means below, like a hypodermic needle goes below the skin. Hypo means below or less than, so it's one less than us. So the baby brother, if you will, of phosphoric acid with two less oxygens is called hypophosphorus acid. The baby brother of chloric acid, HClO, with two less oxygens is hypochlorous. Similarly, we have hypobromous and hypoiodous acids. One last variant here. We actually have a couple of these acids that have what might be described as a big brother, older brother, who has one more oxygen than the normal acid. For example, these are called per-ic acids. Per is the prefix and ic is the suffix. So for example, we have perchloric acid. It has one more oxygen than the ic acid. Perbromic acid, HBrO4, and periodic acid, HiO4. That has to go on the hard drive. You have to memorize. Try memorizing the ic acids and their formulas, and from there it should be easy to add or subtract oxygens and get the rest of it. Now when oxyacids react, they release hydrogen ions, and they leave behind what's called a polyatomic ion, an ion made of more than one type of atom. For example, when nitric acid behaves as an acid and gives up hydrogen ion, what's left when you take H plus away from neutral HNO3? What's left is NO3 minus, nitrate ion. And it has to have a negative charge because this hydrogen ion left its electron behind when it left the nitric acid. So this nitrate has one extra electron, hence a negative charge. This is called a monoprotic acid. I'll define that later. One ionizable hydrogen. Sulfuric acid has two ionizable hydrogens. It's diprotic, or more generally described as polyprotic. If it loses both hydrogen ions, what's left? It would be SO4 with a charge of -2. Another reminder here is that in equations, and these are equations, they have to be equal on both sides, not only in terms of mass, but also a charge. So notice 2 positives and 2 negatives makes 0 charge, which is the same as the left-hand side. Sulfate is -2. And phosphoric acid has 3 acidic hydrogens, or ionizable hydrogens. If it loses all 3, what's left? PO4 with a -3 charge. So if we take away all of the acidic hydrogens from all of the oxyacids, we are left with these polyatomic anions, whose names and formulas you need to memorize. All right, let's look at the names and formulas of the anions of the oxyacids that form when these oxyacids lose all of their acidic hydrogens. The anions have an ate suffix. They end in ate. So acetic acid, losing its single hydrogen ion, forms acetate, and its formula would be CH3COO-, having lost the one hydrogen ion. Carbonic acid with 2 hydrogen ions will lose both of those, forming an anion called carbonate, CO3 -2. For each hydrogen ion removed, the anion charge increases by 1. Nitric acid, HNO3, losing its only acidic hydrogen, would form an anion called nitrate, NO3 minus 1. Sulfuric acid with 2 acidic hydrogens, losing them both, forms an anion called sulfate, SO4 negative 2. Phosphoric acid with 3 acidic hydrogens, after losing all 3, is an anion called phosphate, PO4 negative 3. Chloric acid, after losing its only acidic hydrogen, forms an anion called chlorate, ClO3 negative 1. Similarly, bromic acid forms bromate, and iodic acid forms iodate. Now what about the lesser oxyacids, the us acids? For example, nitrous acid, after losing its only acidic hydrogen, forms an anion that's described by ite, so it becomes nitrite, NO2 minus 1. Sulfurous acid with 2 acidic hydrogens, losing both, forms an anion called sulfite, the end in ite, SO3 negative 2. We're going to skip the phosphorus acids and come back because they are irregular. When chlorous acid loses its only acidic hydrogen, the anion formed is chlorite. Similarly, bromous acid forms bromite, iodous acid, iodite, IO2 minus 1. Now the hypo-us acids, like hypochlorous acid, forms a salt called hypoite. This is hypochlorite, ClO minus. Hypobromous acid, losing its only acidic hydrogen, forms hypobromite, BRO minus. Hypoiodous acid, losing its only acidic hydrogen, forms hypoiodite. Now what about the higher oxyacids, the ones with an extra oxygen? Perchloric acid, after losing its only hydrogen ion, would form ClO4 minus called perchlorate. So a peric acid's anion is a per8. Similarly, perbromic acid, HBrO4, forms perbromate, BrO4 minus. And periodic acid forms periodate, IO4 negative. And that brings us back to the oxyacids of phosphorus. These last two are irregular. The completely deionized anion of phosphorus acid is actually HPO3 negative 2. I will explain in detail later, but just for right now, only 2 of these 3 hydrogens are ionizable. Only 2 can be replaced. There'll always be 1 remaining, unlike the other oxyacids. And so phosphite is actually HPO3 negative 2. H3PO3, phosphorus acid, only has 2 acidic hydrogens. And so phosphite, the anion formed by removal of all of its acidic hydrogens, is actually HPO3 negative 2. And the anion of completely ionized hypophosphorus acid is actually H2PO2 negative 1, which means that hypophosphorus acid only has 1 acidic hydrogen. 2 of these are not removable. They stay with the anion. And so hypophosphite is H2PO2 negative 1. I realize these are different, and I'll go into some detail later to try and make it clear why. All right, so you need to learn these oxyacids and their formulas, so I have some exercises here just to help you try and put them on the hard drive. If you count up the number of atoms present, you can write the formula and name. We see there's 1 acidic hydrogen in this acid, the only one bonded to oxygen. This is CH3. These are non-acidic hydrogens. COOH with 1 acidic hydrogen, that's acetic acid. When it loses its 1 acidic hydrogen, see it's gone, it forms acetate. Here's carbonic acid with 2 acidic hydrogens bonded to oxygen. That's carbonic acid, H2CO3. When it loses both of those and leaves the electrons behind, it forms carbonate, CO3 minus 2. Here's nitric acid with one acidic hydrogen, HNO3. When it loses that acidic hydrogen, it forms NO3 minus 1, which is nitrate. Here's sulfuric acid with two acidic hydrogens bonded to oxygen. That's H2SO4, sulfuric acid. When it loses both its acidic hydrogens, what's left is SO4 minus 2, sulfate. Here's phosphoric acid with three acidic hydrogens, all bonded to oxygens. H3PO4, phosphoric acid. If it loses all three, what's left is PO4 negative 3, phosphate. And here's chloric acid with one acidic hydrogen, HClO3. When it loses it, what's left is ClO3 minus, and that's chlorate. Now I've done this one more time, and this time I've drawn Lewis structures, sometimes called line bond structures. A line bond structure uses lines to show shared pairs of electrons, to show covalent bonds, and it shows the non-bonded pairs of electrons that are also present. So here is the line bond or Lewis structure of acetic acid. Notice again that these three hydrogens are not acidic. They're non-polar covalent bonds to carbon. Only the hydrogen bonded to the oxygen in acetic acid is acidic. And that's why it's monoprotic. It loses only one hydrogen, forming CH3COO minus acetate. Notice that both the hydrogens in carbonic acid are bonded to oxygens, and therefore H2CO3 carbonic acid is diprotic. When it loses both hydrogens, it forms CO3 negative 2. Here's the two negative charges on the oxygens, and that's carbonate. Next is nitric acid, one acidic hydrogen, HNO3. When it loses it, this oxygen gets a negative charge on it, NO3 minus nitrate. Sulfuric acid is diprotic, two acidic hydrogens, H2SO4. When it loses them both, notice these oxygens now have negative charges, and that's sulfate, SO4 minus 2. Here are the three acidic hydrogens of phosphoric acid, H3PO4. All three can be removed, giving us negative charges on each of the three oxygens. That's PO4 minus 3, that's phosphate. And finally, here's chloric acid with one acidic hydrogen, HClO3. When it loses it, we have one negative charge remaining. That's ClO3 minus, that's chlorate. Now there are a few other polyatomic ions that you encounter in first year chemistry. You need to memorize these as well. They're not as difficult as the ones previous. Here's HCN, is called hydrocyanic acid. Now, it's technically called hydrogen cyanide, but it is acidic, and so when you put it in water, it's then called hydrocyanic acid. It's a weak acid and it has a sweet almond odor, but it is highly toxic when ingested. It does ionize according to the following equation, producing a hydrogen ion, as you see here, and what's left is a polyatomic anion, Cn-, called cyanide. Now this is water, and of course water, although its formula looks like a binary acid, we know it's quite neutral. It can be separated using a strong enough base or a reducing agent like a sodium metal. You can remove a hydrogen ion from water, leaving behind an anion, which is called hydroxide ion, OH-. Here it is, and you need to memorize hydroxide ion. Down here we have ammonia, NH3. This is not an acid, it's actually a weak base, moderately weak base, and it can react and gain a hydrogen ion. Ammonia has a pungent odor. It smells that like a Windex or a chicken coop. It's a moderately strong base. When it reacts with hydrogen ion, it forms an ammonium cation, according to the following equation. So take NH3, which is neutral, add an H plus to it. What do you get? NH4 plus. That's ammonium cation. You need to memorize it. Note, please, that ammonium ion is the only polyatomic ion that I've listed that is a cation, and its IUM ending indicates that it is a cation. The polyatomic anions we've been dealing with, they have endings such as ate and ite and ide, and those are anions, but IUM indicates a cation. Here I've drawn them one more time in Lewis structure form to perhaps give you a better appreciation of how they ionize. So HCN is hydrocyanic acid, and the anion formed, Cn- is cyanide. Of course, this is water. When it's ionized, it produces this polyatomic anion called hydroxide OH-. And ammonia, when it reacts with hydrogen ion, H+, forms ammonium NH4+. All right, we need to go a little further into monoprotic and polyprotic acids. Now, acids like acetic acid, nitric acid, and nitrous acid, and perchloric, chloric, chlorus, and hypochlorous, etc., they all have only one ionizable hydrogen per molecule, and they're called monoprotic acids. Mono means one, protic means proton. Note that a proton is actually a hydrogen ion, or a hydrogen ion is actually a proton. In acetic acid, the three hydrogens bonded to carbon are not ionizable. They're nonpolar bonds. Now, acids like H2CO3, carbonic, H2SO4, sulfuric, sulfurous, phosphoric, they can release more than one hydrogen ion per molecule, and they are called polyprotic acids. Specifically, this polyprotic acid is diprotic. Sulfuric acid is diprotic, as is sulfurous, but phosphoric acid is actually triprotic. In any case, when polyprotic acids ionize, they can lose one hydrogen ion at a time. And that gives rise to some other polyatomic anions whose names and formulas we need to figure out and memorize. So, for example, carbonic acid is diprotic, but when it loses only one hydrogen ion, what is left? Well, HCO3 -1 is what's left. That's a polyatomic anion is called bicarbonate or monohydrogen carbonate. There's one hydrogen in it, hence monohydrogen carbonate. The bicarbonate means half neutralized. So in the English language, the word bi sometimes means half. For example, if you get paid bi-monthly, you get paid every half month. Bicarbonate is half neutralized carbonic acid. Now, bicarbonate can further be neutralized or ionized, forming then carbonate. Similarly, sulfuric acid is diprotic. When it loses only one hydrogen ion, what's left? Well, HSO4 -1. And again, I want to remind you that these are equations, and they must balance, they must be equal in terms of mass and charge. The charge on the left side is 0. Sulfuric acid is neutral. The charge on the right must also be 0. +1 and -1 makes 0. This half-neutralized sulfuric acid anion is called bisulfate or monohydrogen sulfate. When bisulfate further ionizes, it produces sulfate anions. Similarly, sulfurous acid is diprotic. Upon ionization, a single step would produce what? HSO3 -1, which is called bisulfite or monohydrogen sulfite. And when bisulfite further ionizes, it forms sulfite. And finally, let's look at the phosphoric acid sequence. It's triprotic. When it loses one hydrogen ion, what's left? H2PO4 -1. This is not biphosphate. Bi means half. Half of 3 is 1.5, and you can't have 1.5 ionization. So do not use the prefix bi for phosphate anions or partially ionized phosphoric acid. This is called dihydrogen phosphate. There's two hydrogens and a phosphate. Now, dihydrogen phosphate still has two replaceable hydrogens. When one more is lost, what's left? HPO4 -2. We've taken away two hydrogens, so HPO4 is -2. That would be called monohydrogen phosphate. And when monohydrogen phosphate further ionizes, what's left is PO4 -3, which is phosphate. So here I've drawn the stepwise ionization of some of the polyprotic acids to help you better get a hold of what's going on. Perhaps this will help you memorize the names and formulas. Here we see the 3 acidic hydrogens of phosphoric acid, H3PO4. Upon losing just one of them, the one on the right in this case, then that oxygen now retains the electron it used to share, so it's negatively charged, and this is H2PO4 negative 1 dihydrogen phosphate. When dihydrogen phosphate further ionizes, it loses another hydrogen ion, say for example this one here, leaving the electron behind. It is now HPO4 negative 2 charges, and that's monohydrogen phosphate. Monohydrogen phosphate has one less acidic hydrogen. When that leaves, leaving the pair of electrons that are shared behind, then we get phosphate, PO4 negative 3 negative charges. We can do the same rationale for sulfuric acid, 2 acidic hydrogens, H2SO4, it loses 1. What's left is HSO4 negative 1, bisulfate. And bisulfate, HSO4, can further ionize, producing SO4 negative 2, sulfate. All right, similarly, sulfurous acid, H2SO3, when it loses a single hydrogen ion, will form HSO3 with a negative 1 charge, and that's called bisulfite. So now that we've learned some of the polyatomic ions, we can use them to write names and formulas of chemicals involving them. Compounds containing polyatomic ions are named the same as binary compounds. Formulas containing polyatomic ions are written the same as binary compounds with one difference. Sodium chloride is NaCl and calcium chloride is CaCl2. Note that parentheses are not placed around monatomic ions like chloride here, even when there's more than one of them present in the formula. That's a monatomic ion. But here's some polyatomic ions. The hydroxide ion is polyatomic. Sodium hydroxide's formula is NaOH. But calcium hydroxide is CaOH taken twice in parentheses. So parentheses are placed around polyatomic ions like hydroxide, but only when several are present. So not in the case of NaOH where there's only one, but they are required when there's more than one group. You see, if you left this bracket out, the formula would be CaOH2, which is not correct. You have to have 2 oxygens and 2 hydrogens, but only apply the parentheses when there's more than one group present. A couple other interesting polyatomic ions. Ammonium hydroxide is a compound made of an ammonium polyatomic cation and a hydroxide polyatomic anion. One more here is ammonium cyanide. Notice the nitrogen occurs twice, once in ammonium and once in cyanide. Now, they do remain separate, so we can recognize the ammonium cation and the cyanide anion. You wouldn't want to combine them together and write something like N2H4C. Please keep the identity of each polyatomic anion clear and separate. All right, so here's some practice writing the names or formulas using the stock system, and I would recommend you write ions and their charges to help you do so. First case, zinc is always +2, acetate is -1. We'd need 2 acetates for each zinc. In this example, acetate we did notice is -1, and there are 3 of them. That makes iron +3, so the name would be iron 3 acetate. We have to state that it's +3 because iron has more than one oxidation state, whereas zinc only had +2, so it's not stated. In the next example, we have nitrite ions, 6 of them, so that's -1 times 6. That makes chromium +6, so we write chromium 6 nitrate. Next we have manganese 7 nitrate. Nitrate is -1. The name tells us manganese is +7. That gives us the combining ratio of 7 nitrates for every manganese. Aluminum sulfate is simply aluminum and sulfate. Use the inverse rule to combine them to Al2SO4 taken 3 times. Aluminum bisulfate. Bisulfate is -1, aluminum is +3. That means we need 3 bisulfates for every aluminum. Make sure you put this in parentheses. Potassium and sulfite is simply potassium sulfite. This species is bisulfite. Its charge is -1. The formula says there's 2 of them. That makes iron +2, iron 2 bisulfite. Nickel 2 perchlorate. Nickel is +2, given in the name. Perchlorate is ClO4 -1. Therefore, the combining ratio is 2 perchlorates for each nickel. Here we have tin and chlorate. Tin is, well, we're going to figure it out. Chlorate is -1. The formula says there's 2 of them. That means tin has to be +2. So the name is tin 2 chlorate. Here we have lead 4 and chlorite. That gives us the combining ratio PbClO2 taken 4 times. In the next example, we have mercury and hypobromite. Now, hypobromite is -1, and since there's only one mercury, it must be +1. Therefore, the name is mercury 1 hypobromite. Next, we have cobalt 3 bromate. Cobalt is +3, bromate is -1. Therefore, the combining ratio must be 3 bromates for each cobalt. And chromium 3 perbromate. Chromium is +3. Perbromate is BrO4 -1. That tells us we need 3 perbromates for each chromium, BrO4 taken 3 times. Some more examples. Strontium iodite. Strontium is in group 2A, iodite -1. So the combining ratio is SrIO2 taken twice. Here we have ammonium ion and sulfate. So the name is simply ammonium sulfate. Next example, we have lithium and hypoiodite, both with a charge of 1 in magnitude. They have combined in a 1-to-1 ratio, simply LiIO, lithium hypoiodite. Beryllium is always +2. It's in group 2A, simply beryllium iodate. Copper 2 bromite tells us, the name tells us copper is +2, bromite is -1, so therefore I need 2 bromites for each copper. Next one is aluminum and carbonate, so that's simply aluminum carbonate. Copper 2 bicarbonate, +2 and -1, Cu, HCO3 taken twice. Next we have barium and phosphate, so that's simply barium phosphate. Barium has a fixed oxidation number of +2 because it's a group 2A metal. Cadmium also has a fixed oxidation number of +2, and per iodate is IO4 -1, so there's the formula CdIO4 taken twice. Next we have tungsten and cyanide. Now cyanide is -1. The formula says there are 6 of them, therefore tungsten must be +6. The the name is tungsten 6 cyanide. Next we have molybdenum and carbonate. Now carbonate is -2, and molybdenum 6 is given, so we know the charge is +6, therefore the ratio would be 3 carbonates for each molybdenum. V2, SO3 taken 5 times. Well, sulfite, SO3 -2, has a charge of -2, and there are 5 of them for a total negative charge of -10. And divided by 2 gives me a total positive charge for each vanadium of +5. You could also use the inverse rule, reverse there, and we would name that as vanadium 5 sulfite. Next we have platinum 4 phosphate, so platinum is +4 from the name, phosphate's -3. Use the inverse rule and write the formula as shown. And finally we have mercury and bisulfate. Now bisulfate we know is -1, and the formula says there are 2 of them, therefore mercury must be +2, mercury 2 bisulfate. Now, in most oxyacids, adding or subtracting oxygen to a formula does not change the number of ionizable hydrogens. For example, nitric acid has one ionizable hydrogen, and so does nitrous. They're both monoprotic. Sulfuric and sulfurous are both diprotic. And perchloric, chloric, chlorous, and hypochlorous, they're all monoprotic. Different numbers of oxygens, but same number of hydrogens. But the oxyacids of phosphorus are unique. See, H3PO4, phosphoric acid, is triprotic. But phosphorus acid, H3PO3, is actually only diprotic. It only has two of these hydrogens are acidic. And further, hypophosphorus acid, H3PO2, is only monoprotic. It only has one acidic hydrogen. Two of these are not acidic. So let's examine the structures of the oxyacids and note which of the acidic hydrogens are bonded to oxygen. The acidic hydrogens are not bonded to phosphorus. So here is phosphoric acid. All three of its hydrogens, which I've colored red, are bonded to oxygens. They are all acidic. Hence, phosphoric acid is triprotic. But phosphorus acid is only diprotic. It only has two acidic hydrogens because this third one, colored blue, is actually bonded to phosphorus. And this bond is a nonpolar covalent bond. It's not easily broken. Hypophosphorus acid takes it to the next level, if you will. It's only monoprotic. It only has one acidic hydrogen. Two of the hydrogens are bonded directly to phosphorus, not to oxygen. So here I'm showing the stepwise ionization of the oxyacids of phosphorus just to try and reinforce this. So here we have three acidic hydrogens on phosphoric acid. And after losing one hydrogen, we're left with dihydrogen phosphate with a charge of -1. On losing another hydrogen, we get monohydrogen phosphate with a charge of -2. And losing the final acidic hydrogen gives us phosphate PO4 -3. But compare phosphorus acid H3PO3. Notice two of the hydrogens are bonded to oxygen and are acidic. One is not acidic. So there's phosphorus acid. When it loses one hydrogen ion, what's left? Well, here I've lost one hydrogen. I have H2PO3 with a -1 charge on one of the oxygens. And that's called dihydrogen phosphite. That makes sense? Dihydrogen phosphite. When it loses its last and final acidic hydrogen over here on the other oxygen, what's left is HPO3 -2. This remaining hydrogen is not replaceable, it's not ionizable, it's not acidic. What's left is called monohydrogen phosphite, or it can simply be named phosphite. Why is that? Well, in the same way that phosphate means phosphoric acid having lost all acidic hydrogens, similarly phosphite means phosphorus acid having lost all of its two acidic hydrogens. So you have a choice of naming it either way. The final example here is hypophosphorus acid. It has only one ionizable hydrogen, the one attached to the oxygen. These two are not ionizable. When it loses its one and only acidic hydrogen, what's left? Well, it's H2PO2 -1. That would be called dihydrogen hypophosphite, or you can simply call it hypophosphite. Why? Because hypophosphite is hypophosphorus acid after losing all of its acidic hydrogens, its one and only, in the same way that phosphate means phosphoric acid after having lost all of its acidic hydrogens. So we have some options here. And let's get some practice. So we've seen there are several conventions for naming the anions of partly ionized polyprotic acids. What do I mean? The student, you have some latitude here. However, any correct name must identify the compound unambiguously. So try naming the following compounds using more than one correct name. H3PO4, we know it to be phosphoric acid, or it could be called hydrogen phosphate, though that's a little awkward. How about the next one? We have sodium and dihydrogen phosphate present. So you could name this as sodium dihydrogen phosphate. You don't have to say how many sodiums. It would be understood there can only be one because phosphate is -3. We have two positive charges from the hydrogens. That means there can only be one more sodium. One could also write the name monosodium dihydrogen phosphate. That's perfectly correct, although a bit cumbersome. And it is also acceptable to say monosodium phosphate and not even list the hydrogens. It's understood that sodium is +1, phosphate's -3. There must be 2 more hydrogens in this compound, so you'll often see it written in this fashion. Try the next compound. Got potassium and monohydrogen phosphate. How do we name this? Several ways. We could say potassium monohydrogen phosphate is perfectly correct. You could also write dipotassium monohydrogen phosphate. It's correct, although cumbrous. You could also write simply dipotassium phosphate, leaving out the hydrogens, because if we've identified that there are 2 potassiums, we know phosphate is -3, there has to be 1 hydrogen left over. We have 3 ways to name it. How about the next one? We have lithium and dihydrogen phosphite. How do we name that? We could say lithium dihydrogen phosphite. We could say monolithium dihydrogen phosphite. Again, it's cumbrous. Or we could even just say monolithium phosphite. Now, by saying monolithium, we know that's +1, and we don't have to list the 2 hydrogens that must be here. It's unambiguous this way. Monolithium phosphite. Next example, I have silver and monohydrogen phosphite. How do I name that? Well, I could say silver monohydrogen phosphite. That's perfectly correct. You could also say disilver monohydrogen phosphate, or you could simply write silver phosphite. Now, by saying silver phosphite, we know that phosphite has completely ionized. It's HPO3 -2. And we're saying that everything else is silver. So we could put the formula together from there. You could also say disilver phosphite, and that would work as well. So there's several options here. As long as it's unambiguous and clear, it's acceptable. Next example, we have sodium ion and dihydrogen hypophosphite. So how do we name that? Well, we could say sodium dihydrogen hypophosphite. That's correct. You could say monosodium dihydrogen hypophosphate. That's clear. You could also say sodium hypophosphite. Now, by saying sodium hypophosphite, well, hypophosphite is H2PO2, it's -1, it's completely ionized. So therefore, there can only be 1 sodium present. It's not necessary to say monosodium hypophosphite, although that would be acceptable as well. Next example, we have ammonium and monohydrogen phosphate. So we could say diammonium monohydrogen phosphate. We could simply say diammonium phosphate. Since we know ammonium is +1 and there are 2 of them, there must be a hydrogen present. One could even say ammonium monohydrogen phosphate. So you have 3 options there. All right, let's carry on. We got ammonium ion and monohydrogen phosphite. How do we name this? We could say diammonium monohydrogen phosphite, perfectly correct. We could say ammonium phosphite because we know phosphite is completely deprotonated phosphorus acid with a charge of -2, which tells us there must be 2 ammoniums. You could say diammonium phosphite as well. Here we have ammonium and dihydrogen phosphate. How would we name that? Well, we could say ammonium dihydrogen phosphate. You could say monoammonium dihydrogen phosphate, or you could simply say monoammonium phosphate. We would understand there must be 2 additional hydrogens because ammonium has a charge of only +1 and phosphate is -3. And finally, we have ammonium, potassium, and phosphate. Now we could say diammonium potassium phosphate. We know there must be 1 only because there's 2 ammoniums. You could say diammonium monopotassium phosphate. You could say ammonium monopotassium phosphate. So several options there as well. I just ran out of space. Now, you've seen then that the number of hydrogens does not need to be stated, provided that the number of other cations is explicitly stated in the name. Now there is a caution here. We've been using prefixes like di or tri in these partially ionized polyatomic anions, but they should not be used outside of this context. For instance, you would never say calcium dichloride or aluminum trichloride. You do hear that from time to time, but it is not correct form for the stock system. Reserve these prefixes for these partially neutralized polyatomic acids, and an example that we'll see very shortly. Alright, so I know this is difficult. Here's the last difficult part of it. For compounds of monovalent cations like lithium and sodium and potassium and ammonium, etc., we have seen that there are several acceptable names. For example, K2HPO4 can be named dipotassium monohydrogen phosphate. Or you could say potassium monohydrogen phosphate. Or you could just say dipotassium phosphate. They all work. They're all clear. However, when polyvalent metal cations like calcium and aluminum are combined with partially ionized acids, the convention, the rule, is to state the number of hydrogens but not the number of polyvalent metal cations. Here's some examples. Hope it clears it up. So here we have calcium. It's a polyvalent metal cation and a dihydrogen phosphate. How will we name it? You're going to say calcium dihydrogen phosphate. That is clear, unambiguous. We would not say monocalcium. Remember, polyvalent metal cations, they're not numbered in names. You state the number of hydrogens if necessary. How about the next one? Here's calcium and monohydrogen phosphate, so it's simply calcium monohydrogen phosphate. And we have to figure out the number of calciums. You couldn't write calcium hydrogen phosphate, that would be ambiguous. You must identify the number of hydrogens present, from which we figure out the number of calciums in the formula. Next we have an aluminum ion and dihydrogen phosphate. How do we name that? Just say aluminum and then state the number of hydrogens, aluminum dihydrogen phosphate. Next example, I have aluminum and monohydrogen phosphate. Notice that there are two aluminums, but do not say dialuminum. It's simply aluminum monohydrogen phosphate. That is the convention. Here is iron 3 monohydrogen phosphate. So the formula for that would be, we would use our inverse rule, cross over the 3 and the 2, you'd need Fe2HPO4 taken 3 times. For tin 2 monohydrogen phosphate, we have tin 2 and HPO4 minus 2, combining 1:1 ratio SnHPO4. Lead 4 dihydrogen phosphite, there's lead plus 4, dihydrogen phosphite, so we need 4 of those. And you see, it's really important, even for older chemists like myself, to write down these formulas, the ions, to put it together in the name. You'll have far fewer mistakes and much more success if you take the time to write out the anions and their charges before you put it together or decode the name into the formula. Alright, here we have not Pb but Pd, and that's palladium plus 4 and dihydrogen hypophosphite. So we put that together as palladium 4 dihydrogen hypophosphite, or simply palladium 4 hypophosphite, because recall, hypophosphite means that all hydrogens are removed and 2 will remain. So we don't really have to say dihydrogen. It's understood when we say hypophosphite. And lastly, here we have palladium again and dihydrogen hypophosphite again. This will be palladium 2 dihydrogen hypophosphite, or we simply could say palladium 2 hypophosphite again, because hypophosphite is H2PO2 minus, and it tells us all we need to know to figure out the ratio of all the ions present in the compound. Now that was difficult, and that's about as hard as it gets. So let's get some general review here. Oxidation numbers and charge first. Magnesium is plus 2, acetates minus 1, so we need 2 acetates per magnesium. Got ammonium and sulfate, it's simply ammonium sulfate. We have iron 3 and carbonate. Use the inverse rule and write the formula 2 irons for every 3 carbonates. This is simply barium and nitrate. The name is simply barium nitrate. Do not list the oxidation number because barium has a fixed oxidation number of plus 2. It's in group 2A. Manganese 7 chlorite. We can work out the combining ratio from the charges. That would be MnClO2 taken 7 times. And we have CdIO4, that's cadmium with a fixed oxidation number of +2, and periodate with a fixed oxidation number of -1. It's simply cadmium periodate. And aluminum anhydride have fixed oxidation numbers, so it's simply AlH3, and it's just aluminum hydride. Likewise, beryllium has a fixed oxidation number, so it'll simply be beryllium nitride. Mercury 2-hypobromite, the name tells us the oxidation number of mercury. We know the oxidation number of hypobromite. We can get the formula. We need 2 hypobromites for each mercury 2 ion. Remember that you need to learn the names of the oxyacids. This is sulfurous acid. This next one is HClO3, chloric acid. In this compound we have ammonium ion and monohydrogen phosphate, so you'd name this as ammonium monohydrogen phosphate, or you could say diammonium phosphate, or you could even say diammonium monohydrogen phosphate. Any one of those three is clear and unambiguous. And finally here we have zinc, which is +2, and dihydrogen hypophosphite, so we name that as zinc dihydrogen hypophosphite, or zinc hypophosphite, remembering that hypophosphite is the specific anion. We would not state mono zinc because it's divalent, if you recall. All right, almost done. A few other common acids are encountered in first year chemistry. I want you to study the structures and names of these acids and their anions. I promise they are not as difficult as the ones we've had before. For example, here we have something called permanganic acid. It's HMNO4. Reminds us of perchloric acid. It's much the same. What's important about it is the anion that forms when it loses its hydrogen ion. What would it be? Well, then it would be MnO4 -1. This permanganic acid is monoprotic. It's potassium salt. Potassium permanganate is particularly useful in the lab. It's a dark purple colored reagent used as a strong oxidizing titrant, as you will see. Now, manganese in this compound is in its highest oxidation state of +7, which you could work out. If you're not clear, you should look at my video on oxidation numbers. Just Google it, search it, oxidation numbers on YouTube, you'll find it. And it's this high oxidation state that contributes to the strength of permanganate as an oxidizer, along with the high number of oxygens attached. Here's another oxyacid that I'd like you to learn. This is called chromic acid, H2CrO4. It's used as an oxidizer, particularly in organic chemistry. When you remove 2 hydrogens from it, what would be left would be CrO4 -2, which is described as being chromate. Again, the ic acid is the 8 ending. The per-ic acid is the per-8 ending. It follows the same rules. So chromic acid, H2CrO4, is a diprotic acid. It's a strong oxidizer. Its potassium salt, potassium chromate, K2CrO4, is used as an indicator for the measurement of chloride by silver nitrate titration. You will no doubt do this procedure. Now, in these compounds, chromium is in its highest oxidation state, +6, which again contributes to its strength as an oxidizer, along with the large number of oxygens attached to it. And the third and final example here looks pretty scary, but don't let it scare you. This is dichromic acid, H2Cr2O7. What's important about it is when it loses its 2 acidic hydrogens, it forms an important anion that we encounter from time to time called dichromate. So if you take away 2 acidic hydrogens, what's left is Cr2O7 -2. Dichromic acid is another strongly oxidizing diprotic acid. Its potassium salt, called potassium dichromate, is a common lab reagent. Can you calculate the oxidation number of chromium in it? I'll leave it with you. So here are some pictures just to help you learn these. Potassium permanganate. KMNO4 is a very dark purple crystalline solid. It's so dark purple that it actually looks black to look at. The permanganate ion, MnO4 -1, is released when this is dissolved in water, and it gives rise to bright purple solutions. Potassium chromate is a bright yellow crystalline solid. Its aqueous solutions of this reagent are bright yellow owing to the presence of the chromate ion, CrO4-2. And finally, this is potassium dichromate, K2CrO2O7. When dissolved in water, it releases the dichromate ion. And some practice using these special polyatomic anion names. So here we have iron +3 and permanganate. Now how do we know it's iron +3? Well, permanganate is -1 and there are 3 of them, so iron must be +3. So we name it as iron 3 permanganate. Here we have silver ion, which is always +1. Chromate is -2. The formula therefore would be Ag2CrO4. Zinc is always +2. Dichromate's -2. They'll combine in a 1-to-1 ratio. The name of the compound is simply zinc dichromate. Don't say zinc 2 because zinc, like silver, only has one oxidation state. And like aluminum for that matter, here's aluminum and chromate. Use the inverse rule and you can calculate the combining ratio in the formula Al2CrO4 taken 3 times. Na2Cr2O7, that's sodium ions, and dichromate, that's simply sodium dichromate. Here's vanadium 5 dichromate. Put those charges together and write the formula V2Cr2O7 taken 5 times. Here's Mn2SO4 taken 7 times. Well, we could use the inverse rule to figure out manganese is +7. So we have manganese 7 sulfate. What about chromium 6 phosphate? Chromium +6, phosphate's -3. You're going to need 2 phosphates for every chromium. Here's the formula CrPO4 taken twice. MnO4 taken 6 times. Looks scary, but just break it down. Permanganate is -1, and there are 6 of them. Therefore, molybdenum must be +6, so this is named molybdenum 6 permanganate. Cadmium is always +2, peridates -1. The formula is CdIO4 taken twice. Cobalt, we can calculate it as being +3 because bromate is -1, and there are 3 of them. Hence, this is cobalt 3 bromate. Here we have nickel 2 chlorite. Nickel's +2, chlorite's -1, so the formula is NiClO2 taken twice. And here we have magnesium, which is always +2, and hypobromite, hence we have simply magnesium hypobromite. Well, a big congratulations is in order. You just completed Inorganic Chemical Nomenclature Part 2 on polyatomic compounds. If you learned this material, you should have a very thorough grasp of basic inorganic chemistry nomenclature. Now, there's also a previous video dealing with the nomenclature of binary compounds. You should have really watched this one first, but it's never too late. If you haven't, you can still search for it on YouTube under the name Inorganic Chemical Nomenclature Part 1, Binary Compounds.